Good afternoon. I'm Jason Roberts from the Marine Geospatial Ecology Lab at Duke University. Today I'll be speaking with you about changes in right whale density in the U.S. and Southeast Canada. But first, I'd like to acknowledge my colleagues at Duke, Rob Schick and Pat Halpin, and our collaborators across the many organizations who contribute data and expertise to this effort. Many thanks to you for your contributions, and we hope this project is a worthy outcome of your hard work. Thanks also to our funders, the Navy, NOAA, NROC, and MARCO, and to the Right Whale Consortium for the opportunity to present this project. We at Duke lead several collaborations that aim to produce density maps to help understand the spatial distributions of marine mammals and quantify the potential effects of activities that may harm or disturb them. This process works by combining scientific surveys for marine mammals with oceanographic maps to create models that predict the density of each species. That is, the number of individual animals per square kilometer, from ocean conditions. We also estimate the uncertainty of the density predictions. We use a method called density surface modeling, which has two stages. In the first stage, after survey data are collected and prepared for analysis, we apply a method called distance sampling to model the probability that observers will sight a group of animals based on the distance to the group, the survey platform used, altitude, sea state, and other factors. This allows us to account for animals that were present but not always sighted because they were too far away or the sea was too rough and so on. Also, using data on whale dive patterns reported in the literature, we adjust the data to account for animals that were underwater. After correcting the data for the various factors that affect species detectability across the collaborating survey platforms, we split up the survey transects into segments and link them to oceanographic covariates obtained from remote sensing and ocean models. We then fit spatial models to the segments that correlate observed whale abundance to the covariates. We usually use generalized additive models that allow for nonlinear relationships. Finally, after performing model checks and selecting a final model, we make predictions. To do that, we take a parallel time series of maps of all the covariates and pump it through the model, yielding a corresponding time series of maps of density and uncertainty. We then summarize those into a smaller number of maps, such as monthly means, which are more suitable for use in planning and management applications. In the US, the maps produced by these models have been used in a number of planning and regulatory processes, such as those you see here, which you can find on the internet, or contact me and I'll send you links to the documents of interest. To learn more about the modeling process and obtain density maps for the Western North Atlantic for many cetacean species, you can check out our publications from 2016 and 17. Now, I'd like to talk about the density model we built for right whales over the past year. First, some background. It is now well established that the North Atlantic right whale population entered decline sometime around 2010. As the past decade has progressed, evidence has also accumulated of substantial changes to right whale distribution patterns. In 2017, a synthesis of passive acoustic monitoring efforts across the North American East Coast showed that following 2010, there was a large decrease in acoustic detections at feeding grounds of the Gulf of Maine and Scotian Shelf, simultaneous with a large increase in detections across southern New England and the Mid-Atlantic Bight. This change was observed in visual surveys of Grand Manan Basin at the mouth of the Bay of Fundy. This area was known to be reliable summer and fall feeding habitat for more than 2 decades, but starting in 2010, encounter rate on surveys dropped, and days with no whales increased markedly. Meanwhile, in southern New England, where whales were not known to spend much time in recent decades, whales were spotted feeding in 2010 and every year thereafter. At the calving grounds, the number of members of the population observed south of Virginia during the traditional calving season peaked in 2009 and 2010, and then rapidly fell to levels not seen since the 1990s. In 2019, NOAA approached us about using a right whale density model to assist in developing new U.S. fishery rules designed to reduce the risk that right whales would be entangled in vertical trap and pot fishing lines. We offered them the latest model developed for the Navy, which spanned 1998 to 2016 and was known as version 8, which we presented at last year's consortium meeting. NOAA used version 8 to develop their risk reduction tool, which multiplied whale density by gear density and a gear severity score to produce maps of entanglement risk for different mitigation scenarios. However, they were concerned that the version 8 model would not sufficiently reflect recent patterns in right whale distribution, so they commissioned an update that would incorporate data through the end of 2018. They also requested that we summarize maps into 2 periods, before and after the population entered decline, so that they may be compared and that management measures could be based only on the more recent period. In May 2020, we completed this update in what is known as the version 9 model. At the beginning of October, we made a small revision to correct a problem with predictions for Massachusetts Bay, yielding version 10. Today, I will show you this version 10 model. Here is a map summarizing the survey effort and sightings incorporated into the version 10 model, which spans June 2003 to May 2019. Total effort was nearly 3 million kilometers. You can pause the presentation if you want to inspect the numbers. Time is limited, so I will skip the details of model fitting and go straight to the predictions. But at the end, I'll include a link where you can download a detailed report. Here you see an animation of the summarized predictions. The left spans summer of 2003 through spring of 2010. The right spans summer of 2010 through spring of 2019. These maps show mean density for each month, averaged over the years of these 2 eras. The spatial resolution is 5 kilometers. Sightings used in the model are overlaid as black dots. However, bear in mind that surveying was quite sparse in certain places and times, so absence of sightings does not mean that whales were not there. The central purpose of this modeling exercise is to fill in the blanks as best we can, using a process that standardizes heterogeneous surveys conducted across the region. The model only extends substantially into Canada during July and August, which were the only 2 months for which we had sufficient coverage from US-based surveys used here. We are very interested in collaborating with Canadian organizations to build a joint US-Canada model that can more comprehensively cover the full range of the species. CVs shown here are likely to be underestimates. We're in the process of estimating model uncertainty using a new method, so I'm not going to show uncertainty maps today. From this side-by-side animation of the 2 eras, we can see large changes in density across the region. Here I have summarized the percentage change between the 2 eras for different subregions. In Cape Cod Bay, mean density more than doubled, while it fell by 40 to 50% for the broader Gulf of Maine, except in peak summer when it fell by 85%, when we presume most whales went to areas farther north, such as the Gulf of St. Lawrence. Between Hatteras and Nantucket, mean density more than quadrupled, while it fell by 70 to 80% at the calving grounds. These are large changes. One way we evaluate this model is to compare its predictions to passive acoustic detections. Here is a comparison for the 2010 to 2018 era using data provided by Genevieve Davis at NOAA and her collaborators. Thanks to Jen and the acoustics community for making these data available. On the right is predicted density. On the left are the survey transects in gray and sightings in blue. Overlaid on both maps are acoustic monitoring stations in black and red. A black dot means no right whale upcalls were detected. A red circle means calls were detected, with the size of the circle indicating the percentage of days of the month with detections. From this comparison, we can see that the density model generally captures most of the locations where right whales were detected, but there are important discrepancies. For example, acoustics detected upcalls south of Nantucket all months of the year, but the density model predicted near zero density for July through October. In November, acoustics detected upcalls from Nantucket to Florida, while the density model predicted appreciable density only in the northern part of this region. These differences reflect the lack of effort and sightings available to the model and highlight places and months where additional survey effort might improve model predictions. Our next step is to complete the model uncertainty estimates. Next, we will implement a number of technical improvements and continue to support model users, particularly NOAA, as they drive to complete their latest iteration of the entanglement risk reduction tool. In the longer term, we're pursuing collaborations with zooplankton modelers, acousticians, statisticians, and survey organizations in Canada to build out the data available to be used in the model and the methods used to build it, and hopefully to expand it to more completely cover the species range. For more information, you can download model documentation at the link shown here, or contact me by email. The model predictions are available in GIS formats on request. Finally, we are always in search of information or data that could improve this model. If you know of any, please do not hesitate to contact me. Thanks for your time, and I look forward to our upcoming discussions.